When a new disease emerges and starts infecting people in a population, one of the things we really want to know is whether it's going to continue to spread and infect more and more people, or whether it's eventually going to die out. Some diseases like measles are highly infectious. In a fully susceptible population, each measles case will, on average, infect about 16 to 18 additional people. Something like flu, however, is less transmissible. Each case, on average, would infect between 2 or 3 people. The number of cases that each infectious person generates can vary for different diseases, and we call this number the basic reproduction number, or R0 for short. Now, R0 doesn't depend on how severe the symptoms are, rather it's a measure of how transmissible the infection is, and as a result we can use it to work out what's required to stop an epidemic. One of the ways we can stop epidemics is using vaccination. Now, you might think that to stop a disease you need to vaccinate an entire population, but actually this isn't the case. Of course, if you vaccinate someone, it protects them and stops them from getting infected, but because people who are vaccinated can't pass it on, vaccination also stops the chains of transmission, and that means that this can create a protective barrier which actually stops the epidemic spreading within a population. Say the basic reproduction number of an infection is 2. This means that in a fully susceptible population, each infected person will on average give the disease to 2 other people. But if 50% of the population are vaccinated, each infectious person on average will only be able to give it to 1 of these 2 people, and this means that the epidemic wouldn't be expected to grow over time. This is known as herd immunity. Herd immunity means that as long as a certain proportion of the population is vaccinated, the disease won't be able to transmit within that population. We've seen that if the basic reproduction number R0 is 2, we'd need to vaccinate half the population to stop disease transmission. By the same logic, if R0 is 3, we'd need to vaccinate 2/3 of the population. If we keep going, for highly infectious diseases like measles, we need to vaccinate 17 out of every 18 people, or about 94% of the population, to stop transmission. Herd immunity is especially useful for protecting members of the population who can't be vaccinated, perhaps because they're too old, too young, or have vulnerable immune systems. If they're surrounded by people who have received the vaccine, then that can protect them from infection. If, however, people forgo vaccination, then the herd can no longer protect these people. This means that the population as a whole can be vulnerable to outbreaks. So far, we've just been talking about averages. One of the big challenges in my work is incorporating some of the complexities of reality into these mathematical models. Vaccines are an incredibly powerful public health tool, and the best way to protect populations against disease is to make sure as many people are vaccinated as possible, so we don't run the risk of slipping below this vaccine threshold for herd immunity.